Good afternoon, everyone, or I should say good afternoon if you're in the East Coast or maybe Central U.S. here. But I think maybe good evening to Joe here. But thank you for joining us for our ABC-sponsored webinar, Enhancing Anaerobic Digestion Efficiency Through Thermal Pressure Hydrolysis. I'm Caroline T. I'm going to be facilitating this webinar. Before we begin, I want to give a big thank you to Econward for sponsoring the webinar. Their sponsorship directly supports the ABC and our program, so thank you so much to Joe and his team. And then before we get started and I pass it off here, I just want to go over a little bit of housekeeping. You should be able to hear me. You should be able to see my slides that say quick note. On the right side of your screen, you should have a GoToWebinar toolbar here. I'm going to point out a few things. One, you can adjust your audio at any time based off of what's working best for you. You can switch between computer and phone. Second is our questions pod. Ask questions at any time throughout our presentation. We'll be handling them all at the end of the call, but ask them at any time with that questions pod there. And then the other area to look for is the handout pod at the bottom there. Several of you probably got the email where I sent out our slides for today, but if you did not get that email or you joined late, the handout should be there available to you. The recording, we're going to record this webinar, that and the slides will be sent to you within a few days of this webinar, and they will also be posted on the ABC website for you. So with that, I'm going to hand things off to our moderator for today, Patrick Surtis. He's the Executive Director of the ABC. Patrick, take it away.
Awesome. Thank you so much, Caroline, for putting this all together for everyone. We've got a great crowd here for today, and I know a lot of people that have registered for this, and it's really great to see. And thank you also to Econward for sponsoring this. I'm particularly excited to be able to talk about this topic with you all today because I got to see a lot of the technology that you're going to hear about. I got to see it all firsthand in Madrid just a month or two ago, and I can tell you it's worth learning about, and it certainly has the potential to change our industry. For those of you who don't know who the American Biogas Council are, we are the voice of the biogas industry in the U.S., and we represent over 400 organizations today and about 5,000 people within those organizations that are actively working on biogas projects. If you are not a part of the ABC, you should consider joining us. It's well worth it. Caroline, next one. So I wanted to start out here to give you a sense of where we are in the marketplace here and certainly give some context for Econward's technologies. So we have just shy of 2,400 operational projects all across the country. They're in all 50 states in all sectors, but the potential for 15,000 new systems. And part of what you're going to hear about from Joe today is how their technology, Caroline, I'm getting some feedback here. Thank you. Part of what you're going to hear about today, I think Joe's going to mostly focus on operational biogas systems and how they can benefit if they're taking in additional substrates as one place to focus. And then we'll touch on landfills as a separate opportunity. But I think what you'll learn is that the technology here can work in any biogas system. It just seems that the operational systems that are taking in substrates are the low-hanging fruit. So we'll focus there for this and big opportunity in the biogas industry. Caroline, next slide. So just to give you a sense of who you're talking to today, I think most of you know me as Executive Director of the ABC. Joe Ayala with Econward is the Chief Operating Officer. He's been working in the energy industry, helping to introduce and develop new technologies for over 27 years. So he's in the perfect role for Econward here with their technology, with thermal hydrolysis, using that to basically take like a bag of garbage that you might have from your home or from your business and completely process it in a way that you separate out the non-organics and hopefully do some beneficial things with those. But then in our world, we are very interested in the organics and how much of that organic material you can really take out and be able to do beneficial things with it. And that's where the technology really stands apart, is the ability to separate the organics from the inorganics. And in doing that in a relatively complete sense, it creates opportunities to do other things with those material streams. And to do that from mixed garbage, I think is pretty special. So Joe, I'm going to turn it over to you here to tell everyone more. Please enter your questions as we go along. We'll keep track of them and answer them at the end.
Thank you very much, Patrick. And I think what you say is very important regarding those 15,000 potential biogas projects that we have in this industry. I think this technology, I truly believe this technology will accelerate the process to enable those 15,000 projects. I think we can do it in the next 10 years, maybe 20.
Music to our ears.
I think. So what I will show you guys today, and ladies, I am in Santa Monica right now in California. So it is just past 10 a.m. here. So it's the morning for the West Coast. And what I'm going to show you today is we're going to be presenting a disruptive technology for the anaerobic industry, for the anaerobic digestion industry. This technology will allow for exponential growth of the biogas industry in the next 10 years. We'll be showing at its core is a simple pre-treatment of anaerobic for anaerobic digestion. But that will make the anaerobic digestion process a whole lot easier. It already does. We invented this technology to improve anaerobic digestion with the objective of having a social, environmental, and economic impact. This is not a purely economic pursuit, albeit it is very profitable. We are here to improve our industry, our environment, and ultimately, you know, our society. We want to bring back those good paying jobs, renewable energy jobs to rural America. Next slide, please. So we have been working on this for many years. You can see the company started in 2009. We are just now starting commercialization efforts in North America, but there are many years of work behind this. The company has spent over $60 million getting to this point today, having a mature technology that we can commercialize. Solving the problems of corrosion and abrasion in autoclaving of solid waste. This technology was specifically invented for this purpose. This is not a technology that we are bringing from other industry. This is not a hammer mill or a garlic press that we found to be useful for organic waste. This technology was built for anaerobic digestion, making sure we can continuously treat volumes of solid waste aligned with the demands of our anaerobic digestion processes here in North America, meaning a technology that can really add value to the anaerobic digestion process, not only by separating the physical contaminants, you know, like glass and metals and you know, other contaminants, but also killing all of the pathogens, which is a very important type of contamination. That is really bad for anaerobic digestion and for the digestate that follows. And apart from separating the physical and organic contaminants, it also enhances BMP and HRT. And if you are in the industry, you know this. If you are just new to the industry, BMP is biomethane potential, HRT is hydraulic residence time. This technology will make your projects more profitable and will make anaerobic digestion viable almost everywhere in this country. So those 15,000 opportunities that we see in the US may now be viable projects. Next slide, please. A true social, environmental, and economic impact. This technology will make anaerobic digestion viable at every town in America, even for rural areas of our country. Next slide, please. Early humans learned that cooked food was not only easier to chew and taste better, but also cause fewer stomach aches and digestive issues. The same is true for anaerobic digestion of organic waste. Thermal pressure hydrolysis, pressure cooking, increases the biomethane potential and decreases residence time for a higher energy output of AD processes. There are 4 stages in the anaerobic digestion process: hydrolysis, acerogenesis, acidogenesis, and methanogenesis. The longest and more complex stage of this process is hydrolysis. On a typical anaerobic digestion process with a 28-day residence time, hydrolysis might take 10 to 14 days of HRT, meaning that of your total residence time, over half is dedicated to or maybe half is dedicated to the hydrolysis stage. Now, if we take that stage out of it, if we do it before, then the residence time will fall to probably half. So your residence time that it was 28 may now be 14 days. Next slide, please. We can see here the system and operating parameters. The plant can process about 200 short tons a day, operates with a steam pressure of 58 psig and a temperature of about 300 Fahrenheit, up to 300 Fahrenheit. So these are not extreme operating parameters that we have seen in the old days. These are really low pressures and temperatures when it comes down to autoclaving. Next slide, please. Now we have proved this technology at lab scale, like you can see here, these results, but also a pilot scale, and most importantly, at commercial industrial scale. We are currently operating and processing up to 200 tons per day of waste in our industrial demonstration facility located in Madrid, Spain. A good thing about our first plant being in Madrid is that when we take people for plant tours, we take them to Madrid. Next slide, please. To the right is a picture of our good partner Clamber in Puerto Llano, one of the many places where we co-digest the hydrolyzed biomass coming out from our biomac continuous autoclaving system of those up to 200 tons a day that we mentioned before. Next slide, please. This graph illustrates a process flow beginning with waste on the left and ending with the energy outputs on the top right and digestate for composting on the bottom right. Types of waste include raw municipal solid waste, contaminated source separated organics, pure organics, mere fines, you name it. Everything that has a high organic content you can process here. Obviously, you can also process construction and demolition waste, but you won't get any energy out of it. The EconWare solution is set up as a 5-step system when it includes anaerobic digestion, where the step number 1 will be a pre-screen mechanical separation. Number 2, our proprietary continuous autoclaving system. Number 3, post-hydrolysis mechanical separation. Number 4, anaerobic digestion. And 5, biogas upgrading. The key differentiating aspect of the EconWare solution is a red box, the technology that enables and maximizes the recovery of organics from organic waste. It could be very complex organic waste streams, but it could be very simple ones, just not viable, just not economically viable. Now they will be. Next, please. Now we can see here the industrial setup and details of how the post-hydrolysis treatment looks like, where we can see a light residual separation through a centrifuge and a heavy residual separation through a seditank, a sedimentation process. These are technologies that are very common in this industry. This is the post-treatment is not new. This is just what we did was just to integrate these technologies into our know-how. Next slide, please. We can see here a characterization of a type of waste. In this case, we can see that the waste input had 77% organics, and it had 11% light contaminants residuals and 9% heavy residuals. And you can see there the list of residuals. Yeah, and important to know that when we talk about organics, we are not talking about chemical compounds that contain carbon. We're talking about biodegradable organics that can be processed in an anaerobic digester and produce energy out of them. Yeah, next slide, please. Now, the waste transformation, and a picture is worth 1,000 words, right? You can see on the left your organic organic waste input. In this case, we call this picture on the left in Santa Monica, where we live, and in Los Angeles, where we work, we call this pure source separated organics. That picture on the left, that's how it comes, and that's how it's gonna go to your wastewater treatment plant, or that is gonna go if you buy 100 tons per day of organic waste. That is how it's gonna be. So what you see on the picture in the middle is our machine, our system, and then the picture on the right is the output of the system. Next slide, please. And then once we have the hydrolyzed biomass, we mix it with water and we put it through a centrifugal force system called in this case a twister made by a friends of us, our friends here in North America called Dry Cake. They make this twister machine, and they have sold thousands of these. And this does the separation of the light residuals, and the output of it is the clean light residuals and the hydrolyzed biomass that goes to the next step. Next, please. And then it goes to the seditank, and the seditank is simply a sedimentation tank. Again, Dry Cake makes this. They have sold hundreds of these. They are high output machines, very small. We love them, and we use them a lot. And what it does is to separate all the heavy residuals now. So all your needles will fall in here. Yeah, very good. Next slide, please. And here we see a summary of the average operating parameters. We will give you a copy of this. So, but before we move on, let's look at the VS degradation. That number, which is for people in the biogas industry, is very common. But maybe if you're new, maybe you don't know it. But usually, VS, volatile solids degradation in an anaerobic digestion process goes, up to 50 or 60% or whatever numbers around there. We are getting consistently, when digesting those up to 200 tons a day of organics that we process, over 90% degradation. That right there shows the increase in biogas production. And we get it in 15 days, 15 total days. So if your HRT is 28 days right now, think about it. It could be 15. So moving on to the next slide, please. We obviously, if we produce more biogas, we will have more biogas, also more biomethane in the biogas, right? 68 to 68%. These numbers are consistent. This is not a one-off thing. So you will go from 50 something to 60 something, right? And the next slide, please. And you will get not only an awesome digestate quality, digestate that you can use for land applications and is Class A certified and it's not gonna have heavy metals and everyone is gonna love, and maybe they will pay you a little bit of money to get it of you, but certainly it's a valuable output. And most importantly, because we have killed the pathogens before the feedstock went into your anaerobic digestion, you are not gonna have anaerobic bacterial competition like bad bacteria versus good bacteria. You're gonna have a clean feedstock that is gonna be completely methanogized, metabolized by this anaerobic bacteria that we use, the good bacteria. Next, please. Next slide, please. So this is a summary of our average production data. So now we are not only saying, hey, we got a high biomethane content, we are saying, hey, we have a large amount of biomethane per ton of collected organics. We are getting over 3,000 CAF per ton. We are getting over 3 MMBTU per ton of received organics. And this ton of received organics is the contaminated organics. Remember that organic that had 77% organics only. Think about it. Pull your pen and paper and start doing calculations. 3 MMBTU per ton of collected organics. Next slide, please. Now, we created these 3 scenarios of revenue data where we have 70,000 tons of collected organics per year, but we put 3 different levels of contamination. So 70,000 with 20,000 tons of contaminants, so only 50,000 tons of organics, 60,000 tons, and 100,000 tons. And you can see there the cost per ton, how the cost per ton hovers between 38 when it's highly contaminated to $27 when it's not contaminated. And that's your total cost of ownership for the next 10 years, your total cost of ownership. Look at the net profit between $70 and $80. And this is counting only a mix of, D5 type of RINs. When you go into D3 RINs, this is way higher. And remember, people will pay you money to collect these organics. They're already paying $60 per ton to the local landfill. They will pay you more to produce this. Even if they pay you the same, that's another $60 that you will add to those $70. Yeah, so it's gonna be 130 tons per ton. That's what I'm saying. Biogas industry, friends and colleagues, let's go and look for those 15,000 biogas projects that are out there. Let's make them happen. We have the technology now. Next slide, please. This technology has been demonstrated beyond a conceptual design. It's an industrial technology. It's well proven. It's well developed. It's fully certified. We can see here an example of a process flow sheet for one specific project. Next slide, please. And this is how a whole integrated plant will look like. This is a 600 tons per day capacity receiving pit right there. Each biomac process up to 200 tons a day, making it a 400 tons per day maximum capacity plant. At 95% organics, we will have 360 tons per day of organics, 1,000 MMBTU a day, 360,000 MMBTU per year for this plant. Now, people that know about anaerobic digester will say, hey, I need 10 digesters to have that energy output. No, you don't. Not anymore. Not anymore. Now you can have digesters that are half the size. So with 4 digesters, we can have 360,000 MMBTU per year. Next slide, please. This is very important. We have a very high organic matter recovery, and the reason for that is that we created this technology for this industry. We are not, again, using a hammer mill here or some type of whatever thing that comes from other industry that wasted, because what happens today in organic recovery is that this 3 to 5% for other machines is an order of magnitude higher. It's 30 to 50%. And you need to minimize your organic losses, because these organics, they don't have anywhere else to go, right? They go to landfills, or they are a problem for whoever is collecting the glass or whoever is collecting anything else, right? If they go with the rejected material. Next slide, please. So our value proposition, right? This is a summary of the improvements for AD performance. In summary, we can double your energy output per digester, effectively getting 3 MMBTU per ton of collected organics, contaminated collected organics, with a significantly shorter residence time. We have clients tripling their energy output per digester in certain co-digestion processes. We have developers that are designing smaller digesters, saving half of the capex. And then think about the implications on water consumption. Think about California, think about the dairy industry that is under attack from environmental justice groups because they use too much water. Or think of pistachio growers, that they are under attack because they are using too much water. We will come under attack if we use too much water. We will come under attack if we don't make an efficient use of our resources, of our energy, of our water. This is a technology that you guys need. Next slide, please. A quick return on investment. Obviously, think of a facility that today is operating at 50% capacity. Think of a facility. All of you know several of them that is operating at 50% capacity because of feedstock problems or because of digestion problems or because of whatever problems. If you bring in this technology, you will bring it up back to 70, 80, 100% capacity, yeah? Because you are gonna be able to bring in feedstocks that they cannot bring in today. We hold ISO 9000, 14000, 45,000 certifications, as well as certifications for our production values. We have developed over 4,000 blueprints, 1,500 technical documents. We hold multiple patents and significant trade secrets on the field of continuous autoclaving of solids. We have just been pre-granted another co-digestion patent, soon to be published. Next slide, please. You can see the video on this link here. With hopefully some of you already saw it. And I know that some of you may be asking how many installations you have in the US. We don't have any because we just started the commercialization of this technology, but this is not a green technology. This is a proven technology. Autoclaving have existed for 100 years. Steam was invented a long time ago. We know that cooking is good for digestion. We know those things. We are simply bringing this technology now to this industry because we now consider it mature enough to be commercially deployed. Regarding our first US installation, we expect several to come online at once, as there are no competitors for this technology and developers are trying hard to gain a competitive advantage. We are interested in partnering with companies that can purchase multiple biomass, and our fabrication pipeline is filling up fast, so don't miss out. Next slide, please. Now, I want to switch off to landfills. We love landfills. We can integrate this technology TPH, thermal pressure hydrolysis with AD, and we can put them in landfills. There are over 5,000 landfills. We did a total addressable market study here. We could easily install 1,000 of these in landfills in the US. The green background here could be your landfill with existing landfill gas collection system. We call it the Now One system when it is integrated, but it's simply put an organics capture, an organics recycling facility sitting on a landfill site. This facility will enable landfill owners to secure indefinitely their organic rich municipal solid waste, reduce expensive landfill cell construction and operating costs. This facility shown in the picture is way easier to operate than a landfill with a large gas collection system. 2 people can operate this whole facility. 2. If you're investing in gas collection systems to capture landfill gas for the next 20 years, you should also consider becoming an organics diversion facility, an organics recycling facility, right where you are. We believe this is the landfill of the future. Why not? Let me ask you that question. Why would you landfill today a ton of organics and expect to get biogas for the next 20 years out of it? Why not get all of that biogas in the next month? Even if it is D5 RINs, you're gonna double your revenue. If you're making $5 million today, you're gonna make $10 million a year from biogas, because you're gonna keep your next 20 years of landfill gas collection. The landfill gas collection that is there for the next, it's gonna be producing gas for the next 20 years. You're not gonna touch that. You're just gonna put this one in your landfill site. Next slide, please. So organics arrive to the landfill at the start of phase 1, the aerobic stage where nitrogen and oxygen depletion starts, right? During phase 1, the CO2 content in the gas will increase. In phase 2, oxygen will be consumed at the beginning of the anaerobic stage. Methane generation after landfilling of organics starts at phase 3 during the methanogenic unsteady state. The methanogenic steady phase 4 of the process will continue for 10 or 20 years, what we just said. This means that the landfill will continue to produce landfill gas for a very, 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 very long period of time. And this is what this green line here, this is what landfill owners look at when they are evaluating new projects for landfill gas recovery system, right? Next slide, please. One more click. So now, if we look at the recovered biomethane gas quantities, we were looking at quality before, now we're looking at quantity, they will follow the green line that you are seeing there. Now, one click forward, Caroline. And the red line shows the methane recovered, which starts after placement of the landfill gas collection system. It's important to mention that landfill cells constructions can take several months, up to a year, some say. So during that period, the methane produced is not being captured, right? Next. If we were to have an organics recycling facility, anaerobic digesters co-located at the landfill, a system composed of a thermal pressure hydrolysis combined with anaerobic digestion, like the one shown before, methane will be captured as soon as waste enters the site, right? Here shown in the upper red line. Why we have more gas? You might be wondering. Because we are capturing the full methanogenic potential per ton of biodegradable waste. We are bringing 20 years of gas to right now. Next, please. Now, if we look at the same green line again, but we look at it from biogas revenues now. We looked at biogas composition first, then we looked at biogas quantity, and now let's look at revenue. You know, there are big energy companies acquiring landfill operators and landfill projects because of this green line, right? Because they want to capture that for the next 20 years, right? So next, please. So we will see, and next, please, we will see how the red line follows the green line, right? The revenue will take the same shape when they start producing. Next. But the new revenue brought up by the addition of the organics capture facility will be additional to the existing landfill gas capture revenue. So an organics capture facility, an organic recycling facility does not compete with the existing landfill gas collection system. It does not. It supplements it. It just brings future revenue forward. When we made these calculations, we used D5 RINs. But because we produce double the amount of gas per ton of organics, or triple, we are seeing a projected doubling in the revenue. These systems paid for themselves in 3-4 years, and this system costs $50 or $60 million each. These are not cheap. It's not cheap because they are valuable. These are valuable pieces of technology. This means that installing an organic recycling facility at your landfill will double your current revenue. I think we should leave it here. Next slide, please. And I am looking forward to answering all of your questions.
Thank you, Joe, so much. You know, I think one of the things that really, or not one of the things, but a couple of the things that really impressed me when I saw this on Madrid is the fact that they really have a fully commercial operating plant. We have a lot of developing technology in the American Biogas Council among our members, which is great. We're a growing industry, but it's relatively rare to see things at such a commercial scale working. It's to see stuff fully patented, and the ISO certifications went way deeper than I was expecting them to go, which shows a third-party validation for the technology and the auditing. It's truly impressive. So I'm excited to ask some of the questions here that you all have typed in, and for you all to learn more about this. And I think one of the things we see across the biogas industry is there's lots of opportunity everywhere, and this is certainly one of those places where it seems like it exists. I'm going to start with a couple questions that came in on your parasitic load. So there's a question on what's the energy consumption of the plant and how much water is required for these systems. Could you address that, Joe?
Yeah, absolutely. So we need 1 MMBTU of natural gas worth $5, whatever, to produce 5 to 7 MMBTU of RNG injected into the pipeline. So if the RNG is worth, say, $20 or $40, you do the math, right? So we need we spend $5 in energy to produce 100 or 200 or $300 in energy. In terms of usage per ton, we need 0.2 tons of steam per ton of organics. It's not that much. It's actually really little. And if you look at the video, you will see why that is. It's because we recirculate most of the steam. So we are just adding new steam.
Let's talk about the feedstock going in. Does this require the local jurisdictions sort the trash from residents or commercial facilities?
That's an awesome question. So what happens today is that you have all of the above. You have source separated organics, which are some bins where people is supposed to put only organics, and they will send you that. And those source separated organics may contain up to 30 or 40 contamination. You can get those contracts now with this technology. We will clean them up and we will give you the pure organics. You could get mere fines that are right now being sent to landfills. You can get 100 tons per day from a well-known commercial operation in town, or a well-known institution or a well-known industrial operator. You will get this, hey, we have 200 tons a day of this waste with this characterization. You can do it now. Now you can look at those projects, or you can look at those projects to supplement your current dairy digester project that doesn't have enough feedstock right now, right? We are very good at co-digesting those organics because they're pure and they're hydrolyzed.
We've got a lot of questions here, so which is great here. Following up on that feedstock question, is there a desired total solids range or quantity that you like in the input? From what I saw, you can kind of take just about anything, but maybe there's a desired range.
So this is not can be liquid hydrolysis, liquid autoclaving system. There are people that have been doing that for 30 years, very successful. Some people love them, some people doesn't love them, whatever, but this is not a system for liquids. We don't want to do liquids because we don't want to spend energy hydrolyzing water. Water is already fine as it is. We want solids, so between 20 and 80% solid content, right? You can put a potato or a cow beef or corn stover. Yeah, from 20 to 80% total solids is fine.
So that's really one of the unique things here. I see some questions in here about how this technology compares to other technologies that are out there, but I think that's one of the unique things here, is that you're taking specific processes that are not unique, but what is unique about, like, thermal hydrolysis already exists in different ways, and source separating organic, that all exists. But one of the things that is unique is that you figured out, really, it's the conveyance of the material in a dry form, going through all those cylinders that you saw. It's the conveyance, it's the moving of that material in a dry form that no one else has figured out yet. And also, they haven't figured out in a way that it really lasts, that the corrosiveness won't break down the machinery and break down things. And that's part of why you guys have gotten the
abrasion, right?
Yeah.
Exactly. So we solved two problems: corrosion and abrasion of steam treatment of solid waste. That's a very simple thing. But the iPhone is also a simple thing, right? I mean, yeah.
So I was saying that because I see a few questions in here related to dairy manure and wastewater sludge, and I'll ask them anyway. Can your technology, have you processed a pure stream, like as in uncontaminated by inorganic material, like dairy manure?
Yes. So we have tested dairy manure, but not in the form that you guys have it in a liquid stream. We tested as a solid stream, and it's fantastic. That's fantastic for it. That's fantastic because all of the hydrolysis that you will have done in your anaerobic digester is done before in 20 minutes. So it is fantastic for it. But this is not for liquids. If you already have a liquid stream, this is not for it. If you have a wastewater sludge in your wastewater treatment plant, this is not for that. This is for the solid organics that the municipality and the local regional authority, waste authority, is trying to give you. This is for those additional solid, this is for solid waste, for those solid organics, right? And we process them before they become a liquid stream. Yeah.
So then you would deliver the organics to the wastewater facility or to the farm-based digester, and then allow those to be digested on that site.
What I see happening is that the routes for the trucks are already set up, and sometimes it's way easier just to use the same route and put this facility where you need it. So instead of having the trucks going, say, to a landfill, from the transfer station to a landfill, you can Now send those tracks to your anaerobic digestion facility, and in there you put this pretreatment, you expand your AD, and you can treat it. Or you can put this in a wastewater treatment plant, or you can set up centers, like that's the idea for some large cities where this pretreatment will take place as a solid, and we're going to be moving solids, because moving solids is 10 times cheaper than moving liquids. Why is 10 times cheaper? Because if you're moving a liquid with 10% total solids, that's the amount of total solids that you are moving, right? We prefer to move solids. When you move solids, you save money, you save resources, you save time, you save number of trucks, you save fuel, you save time. Yeah.
So for something like beef cattle manure, where there's often embedded aggregate material in there, do you think that there's an opportunity there for that, or is the sweet spot really with food waste?
I think they are talking about sand bedding contamination
Like sand, dirt, other things like that.
of the manure. I'm not sure this is the best use. There is many more low-hanging fruit that you can. I think the processes that you have to, and there are some new processes to desand the manure now, which are really good. I have my friend Paul Green talking about it. I have heard him talking about it, and from Green Tech plugin from Green Tech Technologies. But there are other systems that are better for those existing problems. I think in the future we are gonna design systems that can co-digest organics. Yeah, we'll have to.
There's some questions here about the gas produced. So one of them goes back to the landfill part that you ended with, asking about the CO2 composition. And I think my understanding is that the CO2 and the methane doesn't change that much with your system. It's the fact that you're pulling volatile solids out of the landfill and getting more methane production from it than you would in the landfill.
So the landfill gas composition today in that landfill for that person may be 55% methane, 45% CO2. I mean, just to generalize. Obviously, there are siloxanes and all kind of other contaminants coming from that leachate, right? What our organics recycling facility is going to produce is totally different. It's going to produce biogas with over 60% biomethane, and the balance is going to be CO2. So if you have 60% biomethane, you only will have 35%, not 45, but 35%. So that's going to make the biogas upgrading much easier and much cheaper. Yeah, but we are not talking about the biogas upgrading system that you have for the landfill gas collection system. That needs to stay, because that is going to be there for the next 20 years and has been properly sized for that production. For the new plant, you will need your own new, because you're gonna effectively triple your biogas production and double your total revenue for the whole site. Hope I answered the question.
And with these questions about the gas content coming out of the digester part of the system, I think, you're saying that anyone can do the anaerobic digestion from the materials. It's really your EconWord system is all the pre-processing that can go in, that pulls the organic material out, and then it's anyone's digestion system, and then based on how you digest that in that feedstock, that's really what determines the biogas content and whether it has oxygen or hydrogen sulfide and all those kinds of things.
It's not going to have oxygen because it's anaerobic. So landfill gas contains a lot of oxygen and nitrogen because they are sucking up, because they have vacuum extraction systems, right? So you get air infiltration into those systems. With our gas, you're not going to have any oxygen, any nitrogen. You're going to have less CO2. So your biogas upgrading system is going to probably cost half per SCFM that what your biogas upgrading system for landfill gas is. And the reason why we get a higher biogas composition is because we have hydrolyzed the biomass those organics. We not only separate all the physical contaminant, we also kill all the organic contaminants, all the pathogens. And because we have hydrolyzed it, per ton of organics, you're gonna get more MMBTU.
Is there a, I guess I misspoke on the oxygen part of it. The question was regarding, is there an oxygen concentration within the reactor, within the thermal hydrolysis reactor?
I mean, it's an autoclaving system. The autoclaving system is not an anaerobic reactor. It's just a pre-treatment. Yeah. So
there's no oxygen added, right? It's just natural air coming in with the material and pressurizing it.
We add is steam. So this is so we open the hopper, the waste comes in with air, I guess, and then we pressurize it with steam, and we do that in a continuous fashion. Yeah. So steam is doing the magic. Steam is the one doing the pressure cooking, doing the thermal pressure hydrolysis. Yeah. This is not a oxygen combustion, or it's not an oxygen reduction. This is none of that. This is just cooking organics so we can digest them easier.
Has there been any, has anyone looked into using poultry manure as a feedstock? And I know this isn't kind of the, maybe necessarily the best use of the system, but has anyone looked into that as we talk about different kinds of manure?
We did, and we are getting like 4 MMBTUs per ton of pure manure. We're getting a crap load of gas, but you know, the challenge is that this system is not designed for liquids, and the way to collect manure, the accepted way to collect manure in agricultural operations is through a liquid collection system, right? So we don't want to make things more complex than what they are already. But certainly, if you have the chance to hydrolyze those solids, you're going to get much more gas, much more quickly. And your biogas plant is going to be way smaller. And it's going to have, you're going to double or triple your return on investment. But that's for new systems, right? For existing systems, I don't know if this is very applicable for existing liquid slurry type of operations. Yeah, it's not.
Talk about what happens to yard waste, paper, stuff that has lignin in it coming into your system.
Yeah, so that's an excellent question. So for green waste, what we call it green waste, there are 2 types of materials. There is the soft greens, like the leaves, the grasses. We can hydrolyze all of that. Now the hardwoods, the you know, the sticks, the hard sticks, the pieces of pallets, that even though we know that it's organics, it's not biodegradable, it's not digestible in anaerobic digestion. So we will separate those.
Let's talk about system sizing and design and stuff like that. Is there a typical size for the system that you recommend?
Yeah, the unit that we are commercializing is about 200 tons per day. And that's the biggest and the smallest units that we have. If you have operations larger than that, you will need multiple systems. If you have operations smaller than that, like say, hey, I only have 100 tons, we need to look at the economics of it. We are seeing right now processes and projects that are economically viable, even with 70,000 tons of pure organics coming into the plant.
What can you say about the current lead time for a system?
It's getting longer, guys. Put your orders in. We're right now we can build a number of these per year, but factories get full.
What can you say about, so the biogas that's produced in terms of the RFS? So this is a question about the RFS and D codes. So the material goes through your thermal hydrolysis system, and then it goes through a digester, and you upgrade it to RNG, and you're trying to sell it as D3 or D5 RINs. What do we know so far about whether the material counts as D3 or D5 RINs, considering that you're taking in MSW at the beginning?
Not always, right? So when we take MSW, say that we set up this facility in a landfill and they are taking MSW, unfortunately that, because it comes from MSW, it will be considered a D3 RIN because of the paper content. The thing is, even if it is D3 RINs, for all the calculations that we have done with clients on landfills, they are still doubling the revenue because they are bringing 30 years of revenue forward. That's one concept. Then for source separated organics, which the EPA, CalRecycle, and everyone else consider 100% pure organics because they don't want to look at the contamination, they're going to give you D3 RINs for that, and they will pay you gate fees. But even if it was D5 RINs, you saw the numbers. This is going to pay back by itself in 2 or 3 years. But we want to look at your project.
Can you talk about the patents that EconWord has on your system?
Yeah, we have patents related to the problems that we solved, the problem of corrosion and the problem of abrasion. We have patents related to the invention of a continuous autoclaving system. And we have trade secrets. We have trade secrets related to the material science behind those materials. We have also processing patents. We, as I mentioned before, we have just been pre-granted a co-digestion patent, which means bringing in a new organic feedstock for co-digestion in an anaerobic digestion of a specific kind, obviously. Yeah, we have 4,500 blueprints, 1,500 technical documents. This is not something that another guy and me put together and put this presentation. We have been working for 15 years to get to this point. We have spent over $60 million, and we have waited. Most importantly, we have waited until the technology is certified mature enough for commercialization, which is something I admire from the leaders of this organization. This is now a proven technology that has been just released to the market, and it's going to take no time in become the next the standard. I can bet you there won't be many anaerobic digestions without this process because it's very valuable. Yeah.
What can you say about the ideal solids content for the material coming in? Like, as you're considering material that you would want to take and that you would not want to take, is there a minimum amount of total solids for your
20%.
system?
Yeah, 20%. 20%.
Okay.
Under that you are on the manure sludge, right? And that's why this is not very applicable. Yeah.
Does the parasitic load, does your energy load change significantly? Like, so the total solids go from like 20 to 80% or 20 and much higher. How does that impact the parasitic load, the energy that's needed?
So obviously, the more water you have, the more energy you waste. So the higher your total solids, the more efficient the system is. However, we can make this work with systems with 70, so the system capacity is 200 tons per day at, say, 50% solids. You can also make it work with 70 tons per day at 25% solids, right? Or 35% solids.
This is a question about comparing classic thermal hydrolysis, so wet thermal hydrolysis, to your dry thermal hydrolysis system. This person saying that previous work in the past on thermal hydrolysis shows that there's no increase in volatile solids destruction ultimately. So for wet thermal hydrolysis, but you're obviously showing an increase in volatile solids destruction. Can you explain why that is, or what's happening that's different?
What is happening is that in a liquid system, you are spending a lot of energy to hydrolyze. Say that you have in a liquid slurry system 10% total solids. Of 100% of the energy that you are using, only 10% is solids that you need to hydrolyze. So then the amount of hydrolysis that you're gonna do for a huge amount of energy, it's insignificant. Now, if you have, instead of having 10% solids, if you have 50% solids or 35% solids, then most of your energy is being used to hydrolyze the solids because they are only solids, right? So then, because there is no water slashing around in the system and absorbing all of this heat, you can use that heat to truly pressure cook the organics. Yeah.
Have you tested your system with plug flow dry digestion technology? So dry digester batch system.
We have done studies for dry the dry digester technology is simply a high solids digester system, right? So instead of working at 6, 8, 10, 12, 14% total solids, it works at 25, 30, 35% total, so a much higher content of total solids. So yeah, we have done studies, and we know as a general industry knowledge, we know that liquid wet digestion produce more gas than dry digestion. I don't want to get into that discussion. It's going to be good for them as well, because in dry digestion, you still have the 4 stages. You still have the longest stage being the hydrolysis stage. So if you can decouple that, you will have smaller dry digesters if that's what you have, right?
All right. Final 2 questions. I know we've kind of gone over the hour here, but the attendance and the questions have been strong here. So last 2 here. What post-treatment of the digestate is needed, or what post-treatment of the organic material coming out of your system is needed to even go into the digester?
The digestate is going to be the best digestate that you ever had, because it's going to be free of any contaminants. And the processing of that digestate will be exactly the same that biogas plants do for their current digestate. It's just going to be much higher quality, yeah, and pathogen free.
So as you pull the organics out of like a mixed MSW, you have plastics pulled out, you have metals pulled out. What happens to that material?
That material usually is labbed and picked up by cement kilns and things like that use them for residue-derived fuels, because it's clean. So all of those live residuals go directly to feed ovens that are thirsty for high MMBTU materials. The heavy residuals, they have to go somewhere else, right? Because they are needles and all of that stuff. Yeah. Sand,
awesome.
Stones.
Well, thank you, Joe, so very much. Thank you, everyone, for your attendance and for all your awesome questions. Carolyn, anything you want to add here as we wrap up?
Yep, I would like to remind you all, we have a survey that goes out after our webinars. Please take just a few minutes to fill that out for us. It helps us improve our webinars. Also, please consider becoming an ABC member. You can do so on our website or reach out to us at team@americanbiogascouncil.org if you have any questions about membership. And then we'll see you at Business of Biogas this October. That's also on our website. Thanks, everyone, for attending.
Thanks, Caroline. Thanks, Joe. Thanks, Econwood.
Thank you.
Bye now.